Okay, so I'm going to do the related problem for this, which says determine the inductance of a coil with 90 turns. Whoops, didn't erase that. 90 turns. Length is 1 centimeter long. Diameter is 0.8 centimeters. So that's 0.01 meter. That's 0.008 meters. The radius is going to be half of this. Radius 0.004 meters. So let's put all this in. L equals 90 squared times 0.25 times 10 to the negative 3 times pi times 0.004 squared, all divided by 0.01. So let's do this. 90 squared is 8100 times 0.25 times 10 to the negative 3 times pi times 0.004. Oops, 0.004. 0.000016, all divided by 0.01. This, of course, is 1, 2, 3, 4, 5. So that's 1.6 times 10 to the negative 5th. 1, 2, 3, 4, 5. Well, let's do engineering notation. 6. 1.6 times 16 times 10 to negative 6. Okay, so I got negative 3 and negative 6. That gives me negative 9. So now I'm doing 8100 times 0.25 times pi times 16 times 10 to the negative 9 divided by 0.01. So let's run these numbers through the calculation machine. So 8100 times 0.25 times pi times 16 divided by 0.01, and I got 10,178,760 times 10 to negative 9. That's, of course, 1, 2, 3, 4, 5, 6. So that's 10 times 10 to the 6th times 10 to the negative 9th, which is 10 times 10 to the negative 3, which is 10 millihenries. Now to check my answer and see if it's correct. And indeed, that's correct. The correct answer there. So, all right, so that is example 13.2 and its related problem. All right, a couple of general questions that people had were about, first of all, someone asked, do you always have to have change to get any action out of an inductor, any induced voltage? And the answer is yes. Inductors only respond to change. If they don't change, if there's no change, an inductor is just a piece of wire. It may have winding resistance, okay, have resistance to the fact that it's got all that wire in it, but it does not act as an inductor. It's simply a resistor. Several people asked questions about inductors in series and parallel. And so why do inductors add the way they do? Okay, well, think about this. An inductor is a coil of wire. Okay, the inductance formula is L equals N squared mu A over L. Now, what happens if you go and add another coil of wire right behind it? Imagine I just take this and I extend it, make it longer. This is like a series connection, one inductor connected to another. So you might say, well, hey, L is the length, and the longer it is, the less the inductance. So shouldn't adding in series make the inductance weaker? Well, that makes sense, except there's number of turns. So if there were 100 turns here, and I added 100 turns here, I have 200 turns. So that would be a wash. If you had 200 turns, make it twice as long, twice as many turns, twice as long, that should no effect. But it's number of turns squared. So the number of turns adds twice, is in there twice. So adding the two, so making the inductor twice as long, you get more turns. And so you have more of the loops of wire, and that's why, in the end, you get more inductance. If you put them side by side, which is like a parallel connection, okay? So if I imagine I have them side by side, so the length is the same, all right? And I've, I have to pause. It's easier for me to explain the one than the others. I got to think about this one for a minute. So to think about with parallel inductors, so series inductors are very simple because the same current that goes in the one inductor goes through the other. So it really is just like having making your inductor longer, which increases it because you have more coils of wire, you get more magnetic effect. In parallel, the thing is that the current splits to the two inductors. So you now have a reduced, because the inductive effect is driven by magnetism, you have less current through each inductor, which reduces the magnetic effect. I find that I can't come up with a really good seat of the pants explanation for the parallels as I can for the series. Obviously if I split the current that's going to one inductor into a second inductor, they each are going to have less, your induced voltage and things like that. The effect is going to be less because you have less magnetic field. So the parts are less than the whole. But I don't really feel that is, I can only come up with like a mathematical explanation. I can't come up with a good seat of the pants explanation for sort of why it works this way with inductors. So I hope that works. I'm a lot happier with my seat of the pants explanation for series as I am for my seat of the pants explanation for parallel. Okay, last but not least, I want to do example 13.1. Only one person asked about this one, but I think it's a useful one. And it says, determine the induced voltage across a 1 Henry inductor. That's a big inductor, by the way. If the current is changing at the rate of 2 amps per second. So the equation is very simple. Induced voltage is equal to inductance times change in current over time, which they like to write di dt because it looked calculus-y. Okay, and it is true. So your inductor is 1 Henry, okay, and di dt is 2 amps per second. So this will be 1 Henry times 2 amps per second, which is 2 Henry's amps per second. And if you remember from the thing I did before about Henry is a volt per amp per second, so that leaves us with volts. All right, and so that's 2 volts. Then the related problem says determine the inductance when a current changing at a rate of 10 amps per second causes 50 volts to be induced. So we have, again, V induced equals L di dt. And so we have 50 volts are induced. This is the related problem, L. And then this is the change is 10 amps per second. So I have to divide both sides by 10 amps per second to get rid of this. So this is going to be 5 henries equals my inductance. I'm sure this is right, but I'll check the answer. And indeed, this is correct. All right. Well, there's only one more round of this, okay? On our last chapter that's part of circuits is chapter 14, and that's on transformers. And as they say about transformers, there's more than meets the eye to transformers by